So far, we've looked at questions that involve function values. We've looked at questions that involve limits. In fact, lots of questions that involve limits. And it almost, up to this point, seems that those two things are separate and apart, right? You know, function value, we do one thing. Limit, we might have to do something different. But in this video, we're going to look at the concept of continuity, right? And you know, when you think of the word continuous, you think of something that's seamless. It has no breaks in it. It's just like one, you know, you almost say like one continuous thing, not like in individual pieces or cut up or anything like that. Well, what we're going to do is give a precise definition of continuity and then look at a few examples. And thankfully, this isn't a very difficult concept, and in fact, it's one that's best illustrated, at least initially, by way of graphs. So let's go ahead, and what I'll do, I'm going to draw several graphs and just highlight some key things, in particular as it relates to function values and limits. So I'm just going to draw the horizontal axis and indicate a point. I'll just call it A, right? So, I'm going to draw a graph that does like this, and then like this, and then like that, right? And we've seen graphs like this before. I mean, this in itself isn't new by any means, right? Definitely not new. But what we're going to do is, again, try to put some concepts together. So looking at this, I can say two things for sure. I can say that f of a does not exist, right? And I could also say that the two-sided limit does not exist. So the limit as x approaches a of f of x, whatever that function is, because the limit from the left, right, this, whatever this y value, what it would correspond to, is different from the y value that the function is approaching from the right, right? So the one-sided limits might exist, but not the two-sided limit, all right? So now I'm going to take this, draw another version of it, and then again I'm just going to keep modifying things slightly. So let's say it's like this, but now let me put a dot there, right? So now what we can say is, okay, well, I didn't finish this one. Yeah, this limit also doesn't exist, but now I can modify. Now there is a function value at x equals a, right? So f of a would be whatever y value that corresponds to this shaded in circle. So f of a exists now, but the two-sided limit still doesn't exist, right? So the limit as x approaches a of f of x, that still does not exist. Okay, so now I'm going to, again, modify this ever so slightly. And hopefully, eventually, you see where I'm going. So now what I'm going to do is do this, but still have my dot shaded in up there, right? So now think about what we can say. We can say still f of a exists. I can now say that the two-sided limit exists because the limit from the left and the limit from the right are the same, right? So I could say that the limit as x approaches a of f of x, I can also say that that exists. What I didn't want to get into, I didn't want to get bogged down in too many numbers. That's why I intentionally didn't put any y-axis and any numbers. I just want to say, okay, kind of look at the graph. The only thing I wanted is to have a specific a value there, right? So I could write things like f of a or the limit as x approaches a, and it makes sense, right? So now, but there's one other observation I can make about this third case. is that even though these two things exist, they're not the same. So I could say that the limit as x approaches a of f of x is not equal to the function value, right? And again, we've seen examples of things like this. So the last thing I'm going to do is, I'll like kind of pause the video and think about it for a second. Think of how I'm changing things. And the last thing I'm going to change is this. I'm going to take my dot and fill in that little hole. So I'm just going to fill in that little hole, and then I have this. So I'm just going to draw it like this now, but just for a little bit of emphasis, I'll indicate that, yep, this is the change that I've made right there, right? So now I can update my observations based on this fourth one. I can say that f of a and the limit as x approaches a of f of x both exist, right? Not only that, but they're equal, right? So now the limit from the left, the limit from the right, and the function value are all the same, right? So I'll just say this, and are equal, right? So I mean, just looking at the graph, we can see that there are differences, right? And again, those differences are reflected in the four sets of observations that we made. Starting with this one, where nothing existed. Here, just the function value exists, and then the limit doesn't exist. And here, the function value and the limit exist, but they're different. And then finally, it's like everything just kind of comes together. And when this happens, when the function value and the limit both exist and they're the same, that's what gives rise to this concept of continuity. All right? So let's write it down and say this. So a function, so let x equal a be in the domain of the function, right? Be in the domain of f of x. Once I say that, it takes this possibility out of it, right? Because if I say that a is in the domain, then f of a has to exist, right? So it rules that one out. And eventually what I'm going to do is rule out all these three by saying this as a part of my hypothesis, right? Or actually a part of the definition. So f of x is said to be, is said to be continuous. So that's what we're defining now, at x equals a if and only if these three things occur, right? So again, this is kind of redundant because I say that it's in the domain, but I'm going to restate it, that f of a exists, right? 2, the limit as x approaches a of f of x exists. And then to now rule out any kind of little holes or anything like that, we want that if they're equal. So the limit as x approaches a of f of x is equal to f of a. So if these three things occur, then we say the function is continuous at that specific point, right? So it's referring to a specific point. What is happening at a? Now, we can extend it, right? And we will do that in a second. So this is the definition of continuity. And if any of these things fail, and I indicated how they can fail in those initial sketches, the ones where sometimes one of these things didn't exist or they weren't equal, but if at least one of these things fail to be true, then the function is said to be discontinuous at x equals a. So I could say otherwise, right? So in all other cases, so otherwise, f of x is discontinuous or not continuous. You can write whichever you'd like. Discontinuous at x equals a, right? So again, in words, for a function to be continuous at a point, the function value has to exist. The two-sided limit has to exist, and then they have to be the same. The two-sided limit and the function value have to be equal, right? Now, suppose, for instance, these properties are true not just at a specific x value, but at all values of x in a certain interval, right? Then we say that the function is continuous on that entire interval. So, moreover, if f of x is continuous, right, at each point, right, so at each point in some interval, at each value of x, let's say it that way, so at each value of x in some interval, the terminology or the way we say it, we say that so then f is continuous on that entire interval. Right? And some of those intervals can be open, some of those intervals can be closed, and so forth. But again, so going back to the graphical way of kind of visualizing continuity, it's the fact now that I can draw the graph of a function like this, right? And at every point, if I think of my x-axis like this, at every point a, so a different a, so let's say I have like an a1 here, and then a2 there, and then a3 there, and then a4 there, and then a5 there, and I'll just say dot dot dot. So at all these different values of x, again we can see the same thing. Like if I pick a point here, then I could say, yeah, the limit from the left and the limit from the right, and then the function value are the same, right? And that's true for every point on a graph like this. So that's kind of what this one is saying now, is that this extension of the definition is saying that the concept of continuity can be extended to not just one point or at a specific point, but at a whole set of points on an interval, right? And it's the idea that your graph, it doesn't have any holes in it. It doesn't have any breaks in it. It doesn't have any jumps in it. It doesn't have any vertical asymptotes in it. So when all those things, are non-existent, then that gives rise to the concept of continuity. And here you could see that, again, it's kind of this seamless curve, no breaks, no holes, everything just looks nice and continuous, right? So it turns out that there are different types of discontinuities, right? So in other words, there are different ways that the requirements of continuity might not be met. I illustrated a few of them before. Those were those initial graphs that we drew earlier. But it turns out other things can happen. So let me just. So it turns out there are really three types of discontinuities these functions can have, and let me illustrate all three, and then we'll do just a couple examples and give an important theorem about elementary functions. Okay, so yeah, that's kind of a mouthful. Let's take it one step at a time. So let's briefly talk about the types of discontinuities. Right? In other words, in how, what are all the different ways that the definition could fail? Well, the one that was closest, to our requirements of continuity are ones that look like this, either like this, right, where just a single point is kind of missing. There's a hole there, or there's a hole there, but it's filled in at the wrong y value. So it's like you're trying to hit a bullseye and you missed it, right? So this kind of discontinuity where you have just a hole, just a single point that's missing, these are called removable discontinuities, right? So these are removable discontinuities. And in a removable discontinuity, the two-sided limit has to exist, right? So the two-sided limit exists. You may or may not have a function value, right? So this one doesn't have a function value. You could say, in order for this to be continuous, we would have to change the function value and slide that point right here, kind of fill in that hole, that gap. But in a removable discontinuity, the two-sided limit exists and is either different from, right? So let's write like this. So this would have to exist. So this exists, and f of a either does not exist, right, which is this case, or is different from the two-sided limit. So or differs from the limit, right? But the function has to be approaching a point, whether that point is actually filled in, right, in a different spot or not at all, we still classify the discontinuity as removable. All right? So in one word, if I were to give you one simple word that would correspond to having a removable discontinuity, it's the presence of a hole, right? So there's a hole in your graph. Okay, so that's the first one. And like I said, this is the one that seemingly is closest to being a continuous function. It's just missing at a single point. Now we can worsen the type of discontinuity, if you will. Why would we want to do that? I don't know, just for kicks. But we could do that to again see, to really highlight the different ways a function can be discontinuous. So what's the other way? Well, this one has a few more possibilities. I'll try to draw as many as I can. So you could have something like that, again with no function value. You could have something like this with, again, the function value missing both of those endpoints there. The endpoints like this could be filled in and then that one not. Or have it the other way around. That one not filled in, that one filled in, and so forth, right? So in this case, when you have these the one thing that they all have in common is that the one-sided limits exist but are different, right? So the two-sided limit doesn't exist. When this happens, we describe the function as having a jump discontinuity at that point. So this type of discontinuity, it looks different from this one, and I hope you can see the difference in that the two-sided limit doesn't exist in either or any of these four cases. And this is what we call a jump discontinuity. All right, jump discontinuity. And again, it could be, so I'm not going to describe all these different possibilities in terms of when it's not shaded in at all anywhere, or if it's shaded in at a point different from the two open circles here, or one of the two. And they both can't be circled in, again, because then the function would fail the vertical line test. So you can't fill in both. At most, you can have one of them filled in. But the one thing, as I said earlier, that's consistent amongst all these graphs is that the two-sided limit doesn't exist. So I'll say this. The limit from the right and the limit from the left, these are both finite limits. In other words, they're both actual numbers, right? So these are finite, but not equal, right? And that's what causes the function to kind of jump from one piece to the next. In fact, this is what you'll see in a lot of piecewise functions. Not all of them, but a lot of piecewise functions have these jump discontinuities, right? So the one-sided limits are finite, but not equal, right? And that's what characterizes a jump discontinuity. Now, there's another type of discontinuity. Like I said, there are three of them, and this one is glaringly obvious. Right? You can see it a mile away, even if you don't have good vision. So what does it look like? These are the ones where you have the vertical asymptotes. So I'll draw maybe three of these. You know, so we know what the infinite limits look like, going off this way, going off that way, going down like this possibly. Or it could be split where it goes off the positive infinity in one direction, negative infinity in the other direction. And I'm going to draw a fourth one. I'm going to draw a fourth one. Something that might look very strange to you, but it is entirely possible to have something like this. There is this old saying, and I always cringe when I hear it because it's not true. When you hear that, oh, a function can never touch its asymptotes. That is not true, right? For instance, here's another way the function could have, an infinite limit in one direction, like this, let's say from the left, and then from the right, it could be a piecewise function that looks like this, right? That is actually allowed. As strange as it might seem, you can define piecewise functions where only a half, if you will, like one side goes off to either plus or minus infinity, whereas the other side approaches a fixed number. So at least one of the one-sided limits would have to be infinite, and then that gives rise to what we call either an infinite or essential discontinuity, right? So all four here, and I wanted you to see this one. At first I was thinking I'll just do the three, but no, I think it's important for you to see this, right? Because it does come up in some of those, like trickier questions. But let me say this. So all these four are examples of infinite, or they're sometimes called essential discontinuities, right? And so how do these come about? Well, as I said, at least one of the one-sided limits has to go off to either plus or minus infinity, right? So what we would have to say is this. So either this, right? and or, because it could be both, but I'm just saying at least one of them has to be infinite. So and or the limit from the left, that limit is, infinite. In other words, either plus or minus infinity, right? And again, we know how to identify the infinite limits. That's where we get things like 1 over 0 or 2 over 0. The whole thing that gives us the idea of the vertical asymptotes. All right. So those are the three types of discontinuities. Let's just do a quick refresher. We have the removable ones, i.e. holes, right? Removable. The ones that the function jumps, there's like a finite jump between the two endpoints here. So it jumps from one piece and then another piece. So that's a jump discontinuity. And then our infinite or essential discontinuities. And that's where our function, again, goes off to either positive or negative infinity in at least one of the directions from either side. Doesn't have to be both, right? These are the ones that we see a lot. We don't necessarily see these a lot, but these are definitely allowed. All right? So that's the concept behind discontinuity. So, then the next question is, what sort of questions am I, what am I going to be asked about this? Well, you might be asked to classify based on a graph. Tell me what kind of discontinuities you observe, right? That's certainly a possibility. But here are some other questions that arise in continuity. And in order to answer these questions, there is a nice theorem about those elementary functions. So the polynomials, the rationals, the algebraic functions, the exponential, the logarithmic, the sine, the trigonometric, the inverse trigonometric, all those functions, there is a blanket theorem that will tell you on what interval those functions are continuous, right? But it's related to a specific concept in college algebra. So let me state that theorem and do just a couple examples just to show you, right? So here's our theorem. And this theorem talks about the continuity of elementary functions, right? Now remember, piecewise functions are not considered elementary because they're not formed by the 4 basic arithmetic operations as well as composition. That's not how you form a piecewise function, right? So this theorem does not hold for piecewise. We will handle those as separate examples. But for elementary functions, forgot my S there, this is what it says, and it's a very simple statement, but very profound. All elementary functions are continuous on their domain, right? And this is the concept from college algebra or pre-calculus that I'm referring to. So what this basically says is, if you can figure out the domain of a function, and we talk about a natural domain, we're talking about the set of all values of x, right? Real values of x at which the function is defined. So for your basic polynomials, if you know their domain, you automatically know the values of x for which the function is continuous. Same thing. If you happen to know your domain of inverse sine, then you would automatically know the values of x for which that function is continuous. So knowing the domain allows us to answer this other questions about this other concept that's related to calculus. All right. So just to wrap up this video, let's just do a few simple examples to illustrate this theorem, right? All right, so we'll do maybe 2 examples, and I'll do a really simple one. So here's my first example. So it's 5x to the 6th minus 4x cubed plus the square root of 2 times x minus pi, right? So there is my function, and then I have to ask myself, what type of function is this? Well, if I look at my variables, all I see are positive powers of, or non-negative powers of x, because this term doesn't have an x, but what I can do is I can actually put in an x to the 0 power there, and then look at all these powers of x. So they're all non-negative. So no negative powers, no fractional powers, and the coefficients are all real numbers. Even the square root of 2, that's a real number. Pi is a real number. So this is an example of a polynomial, right? So if I were to ask you, what is the domain of a polynomial, right? Then you'd think for a second and say, well, isn't that all real numbers? Yes, it's all real numbers. Polynomials are defined and therefore, based on this theorem, continuous at all real values of x, right? So what I'm not gonna state it like in the context of domain, but what I'm gonna say is this function f of x is continuous, and then what I'll do is I'll state the interval, and I'll say it like this, is continuous on this interval. All right. So a polynomial function is one type of function that's always continuous. In other words, at every value of x, you're not going to see a hole, you're not going to see a jump, you're not going to see a vertical asymptote, right? Now, what else? Let's look at an algebraic function. And remember, an algebraic function is one that involves roots. So let's say I have the square root of x squared minus 1, right? So now things are a little bit different with square roots, because if you think about it, the domain of the square root, like the basic square root function, it's not defined for negative real numbers, right? If we're working with just real numbers, I can't take the square root of a negative number and then get a real number out. It doesn't work. I'd end up getting some complex number. So this function, which is algebraic, right? Even though you can see a polynomial there, it's under a root, right? And that makes it an algebraic function. And for square roots, for fourth roots, in fact, let me write a little fact over here. If I give you a function that looks something like this, and n is an even number, like 2, 4, 6, 8, any of those even roots, for this root to work, whatever is under the square root must be greater than or equal to 0. So the domain consists of all values of your variable such that that thing, that blue box, which I'm just using as a placeholder, has to be greater than or equal to 0. The reason I like to use the placeholder is that I don't just want to say x or some other thing. It's whatever is under the square root, right? As long as there's no other operation, like there's no division or something else that could possibly cause the function to be undefined. If it's just a root, then what we have to do is figure out all the values of x that makes the part that's under the radical greater than or equal to 0, right? So let's say this. Let's write that statement down. So f of x is continuous, right, when x squared minus 1 is greater than or equal to 0, right? And that's good. That's a good first step. The issue is now, this is not an interval. Like, I can't tell you what values of x just by looking at this. I actually have to solve this inequality and figure out what the interval or intervals are, right? Now, the skill of solving a non-linear inequality, that's what this is. This is a non-linear inequality. It's a little bit harder than the linear inequalities, right? It's because of that square and the powers and stuff like that. However, what I will say is this. If you remember that and we did this earlier on, we use this property, and I'll do it, remind you. When you take the square root of x squared, that ends up being the absolute value of x, right? So I'm just going to show you one method that we can use to solve this particular inequality. I can think of 3 or 4 other methods, but because this quadratic here doesn't have the middle, there's no, the middle coefficient is 0, so there's no x term on this side, we can do this. I can say that x squared would have to be greater than or equal to 1. And then when I take the square root of both sides, I have to use this property. And so it looks like this, right? So the square root of x squared must be greater than or equal to the square root of 1. So do that to both sides. But when I reduce this, because x could be positive or negative, I have to put it as the absolute value of x must be greater than or equal to 1, right? Again, this is an important step that is so often overlooked. And then you have to remember now what to do with the absolute value inequality. And by definition, this inequality leads to 2 possibilities. The only way the absolute value of a number can be greater than or equal to 1 is, these are the 2 ways. Either the number itself is greater than or equal to 1, or the number is less than or equal to negative 1. Let me write that over on the left. So in general, if you have the absolute value of A is greater than or equal to B, where B is a positive number, right? Then this leads to 2 possibilities, right? So either A is greater than or equal to B, or A is less than or equal to negative B, right? Let me kind of break these up, right? But all the stuff in blue here, these are algebraic concepts that we're using to now figure out what the interval. So here would be our final answer, and you can write it as inequalities, or you can write it using the interval notation. So 1 to infinity like this, right? And then your union, and then negative infinity up to and including negative 1, right? So for these values of x, right? So if your x is greater than or equal to 1, this function, this square root of x squared minus 1 is always continuous, right? Similarly, if x is less than or equal to negative 1, this function is also continuous. Let me just end by sketching the graph of this function. It looks like this. It turns out this is an even function. And what happens is this: you have a piece of the function that goes this way, and then a piece of the function that goes, again, like I said, it's an even function, so it's symmetric with respect to the y-axis, right? But what happens is there is no function value for values of x strictly between plus or minus 1. So when you graph it, you don't see anything here. And what that means is the function value doesn't exist. And because the function value doesn't exist, then it can't possibly be continuous at any of the x values in here. So you only have these two, they're sometimes called branches of this function. You have one branch that's going that way, and then another branch that's going that way, right? So what I'm showing you here is the graph of our original function, right? So that's just a couple examples. We'll work through a lot more examples as we go forward, but definitely, think about this concept of continuity and how it relates to domain, and then later on we'll see what do we do with piecewise functions. So a lot more stuff to come. See you then.